Welcome, my name is Dr. DrWedding, and this is DrWedding, DC24. Thevenin Equivalent Circuits. In this video, you will learn what Thevenin's theorem is and how to use it to easily convert any circuit into a Thevenin equivalent circuit. A Thevenin equivalent circuit should not be confused with a Norton equivalent circuit. Norton's circuits will be covered in the next video. If you are confused on what a Thevenin circuit is and what it is used for, then you are not alone. This was carved into a bench in my circuits lab room before I started teaching about 30 years ago, and it is still there. Generations of students have hated this topic, but I never understood why. Give me 15 minutes, and you will thoroughly understand Thevenin circuits. Thevenin's theorem states that if you have a linear circuit made up of voltage sources, current sources, and resistors, it can be converted to an equivalent circuit made up of one voltage source and one resistor. So the circuit on the lower left can be converted to the series circuit on the lower right. The Thevenin circuit and the original circuit will always deliver the same power to the load. This can be demonstrated by simulating both circuits using a website called tinkercad.com. Please note, other than the free account I have on tinkercad.com, I have no other affiliation with them. For more information, please read the disclaimer at the end of the video. A model of the original circuit has been constructed. If you are unsure of how a protoboard works, then this simulation might be a bit confusing. But don't worry too much. You just need to understand that the schematic and the modeled circuit are the same. The Thevenin equivalent circuit has also been modeled. Both circuits have had a current meter attached, so the current through the load can be measured. And a voltmeter has also been added in order to measure the voltage drop across the load. In Simulation 1, the load resistor in both circuits has been set to 1 kilo ohm. You can see that the load current is the same in both circuits. You can also see the voltage across the load is also the same in both circuits. In Simulation 2, the load resistor has been changed to a 10 kilo ohm resistor. As in Simulation 1, the current through the load resistor and the voltage across the load resistor are the same in both circuits. In Simulation 3, the load resistor in both circuits has been changed to 15 kilo ohms. As in the previous two simulations, the current through and voltage across the load resistors are the same. As far as the load resistor is concerned, both circuits are exactly the same. As long as the load resistor is the same in both circuits, the power delivered to the load will be the same. Converting a circuit to a Thevenin circuit only takes 3 steps. Step 1. Find the Thevenin voltage. Start with the original circuit and remove the load resistor, leaving a gap. The Thevenin voltage is the voltage across the gap that was created when the load resistor was removed. Step 2. Find the Thevenin resistance. Start with the original circuit and remove the load resistor, leaving a gap. Replace voltage sources with a wire and replace current sources with an open gap. The Thevenin resistance is the resistance measured where the load resistor was removed. Step 3. Draw the Thevenin circuit. Below is what all Thevenin circuits look like. This is the final answer for all of these types of problems. Thevenin circuits are so easy because you only need to find 2 values, the Thevenin voltage and the Thevenin resistance. Let's start with a demonstration that will convert this circuit to a Thevenin equivalent circuit. Step 1. Find the Thevenin voltage. Start with the original circuit and remove the load resistor, leaving a gap. The Thevenin voltage is the voltage across the gap that was created when the load resistor was removed. Step 1. Find the Thevenin voltage. Start with the original circuit. Then remove the load resistor. Don't worry, you will always be told which resistor is the load resistor. Many people will add an X where the load resistor was removed. The Thevenin voltage is the voltage across the gap that was created when the load resistor was removed. Finding the voltage across this gap may seem intimidating, but it is usually very easy. Start to zip and unzip the circuit from right to left. To zip this circuit, Assume the gap is a load resistor with infinite resistance. If you were going to zip this circuit, you would start by combining R5 in the upper branch and our load. These two resistors are in series, so they are added together. And 7 kiloohms plus infinity is infinity. So the gap just absorbs the 7 kiloohm resistor. If there was a resistor in the lower branch, it would also be absorbed by the gap. This simplified circuit is what you need to solve to find the Thevenin voltage. It is very important to understand that the resistors in series with the gap are removed only when you are finding the Thevenin voltage. The series resistors remain when finding the Thevenin resistance. Start by combining the parallel resistors R2 and R4 and redraw the circuit. The Thevenin voltage is the same as the voltage across R24. So if you can calculate the voltage across R24 in this series circuit, you will know the Thevenin voltage. Also, there won't be a need to unzip the circuit. One way to solve this circuit is to find the total resistance, and then use Ohm's law to find the total current. Then use the total current to find the voltage across R24, which is equal to the Thevenin voltage. Instead of Ohm's law, I prefer to use the voltage divider rule. Using VDR, you can find the voltage across R24, and this is the same as the Thevenin voltage. No matter what method you use, you will find the Thevenin voltage for this circuit is 5 volts. This is why Thevenin circuits are so easy to solve. You do not need to find every voltage and every current. You just need to find one voltage, and you can move on to step 2. Step 2. Find the Thevenin resistance. Start with the original circuit and remove the load resistor, leaving a gap. Replace voltage sources with a wire and replace current sources with an open gap. The Thevenin resistance is the resistance measured where the load resistor was removed. Step 2. Start with the original circuit. Then remove the load resistor. Then replace voltage sources with a wire, and replace current sources with an open. The Thevenin resistance is the resistance across the gap. When you were solving for the Thevenin voltage, you needed to zip from right to left, so the resistors in series were absorbed by the gap. To find the Thevenin resistance, you need to zip from left to right. It is very important to understand that the resistors in series with the gap are not removed when finding the Thevenin resistance, like they were in step 1. To zip this circuit, first combine the series resistors R1 and R3, and redraw the circuit. Combine the 3 parallel resistors together. This will leave 2 resistors in series that can also be combined. The Thevenin resistance is the resistance across the gap, and in this example, the Thevenin resistance is 12 kiloohms. Step 3. Draw the Thevenin circuit. The equivalent Thevenin circuit will always take this form. You just plug the 2 values you calculated into this template. This is the final answer for this problem. Now that you have been introduced to the procedure to create a Thevenin equivalent circuit, let's try another circuit. If you want to try and solve this circuit on your own, pause the video. When you finish, restart the video to view the solution. Example 1. Find the Thevenin equivalent circuit for the example shown here. Step 1. Find the Thevenin voltage. Start with the original circuit. Remove the load resistor and mark the gap that was left behind. Zip the circuit from right to left. The infinite resistance of the gap will absorb R5 and R6. So these 2 resistors are removed. The Thevenin voltage is always the voltage across the resistor that is in parallel with the gap. In this example, the Thevenin voltage is across R4. To find this value, you will need to start to solve this circuit like it was any other series parallel circuit. Start by combining R3 and R4. These resistors are in series and can be added together. R2 and R34 are in parallel and can be combined into R234. If we were solving this circuit and filling in a table, we would combine R1 and R234. And if you feel comfortable solving the circuit this way, then that is what you should do. However, to save time, engineers will often calculate just the important information. We have no need for the current through or the voltage across R1. We only need the voltage across R2, 3, 4. And this can be calculated using the voltage divider rule, as shown here. The voltage across R2, 3, 4 is also across R2 and R3, 4. We have no need for R2, so we will focus in on R3, 4. With the voltage across it and the resistance, the current through R3, 4 can be calculated using Ohm's law. The current through R3, 4 is the same as the current through R3 and R4. We can ignore R3 and focus in on R4. Using Ohm's law, the voltage across R4 is found to be 8 volts. And the voltage across R4 is the same as the Thevenin voltage. So, we now know the Thevenin voltage is 8 volts. Step 2. Find the Thevenin resistance. Start with the original circuit and remove the load resistor. Next, replace all the voltage supplies with a wire and all of the current sources with an open. Start to combine the resistors, working towards the gap that was made when the load resistor was removed. Start by combining R1 and R2. These two resistors are in parallel. After combining the resistors, redraw the circuit. Now combine the series resistors R1, 2, and R3. Then redraw the circuit. And then combine the parallel resistors R1, 2, 3, and R4. Then redraw the circuit. Finally, combine the series resistors R5, R1, 2, 3, 4, and R6. This gives us the resistance across the gap created when the load resistor was removed. This is the Thevenin resistance, and it is equal to 800 ohms. Step 3. Draw the Thevenin circuit. Using the voltage calculated in Step 1 and the resistance calculated in Step 2, the complete Thevenin equivalent circuit can be generated. This is the last example in this video. If you want to try and solve this circuit on your own, pause the video. When you finish, restart the video to view the solution. Example 2. Find the Thevenin equivalent circuit for the example shown here. Start with the original circuit and remove the load resistor. When the load resistor is removed, resistors R4 and R5 are absorbed by the gap. The Thevenin voltage is equal to the voltage across resistor R3 because it is in parallel with the gap. So simply zipping and unzipping this circuit will give us the Thevenin voltage. Starting with circuit A, combine the series resistors R2 and R3. This will generate circuit B. In circuit B, the resistors are in parallel, so there is 18 volts across R1 and R2, 3. We only need the current and voltage for R3, so we will ignore R1. Using Ohm's law, the current through R2, 3 is 20 milliamps. When R2, 3 is broken apart into R2 and R3, the current is copied from the previous circuit. We only need the voltage across R3, so we will use Ohm's law to find it. We will ignore R2. The voltage across R3 is 6 volts. So, we now know the Thevenin voltage is 6 volts. Step 2. Find the Thevenin resistance. Start with the original circuit and remove the load resistor. Replace the voltage supplies with a wire and current sources with an open gap. Next, we can start to combine the resistors. Notice that R1 is in parallel with a wire. Pretend the wire is a resistor named R0. This resistor is 0 ohms. If you combine R0 and R1, you will find the equivalent resistance is 0 ohms. So when R0 and R1 are combined and the circuit is redrawn, R01 is 0 ohms and is just a wire. R2 and R3 are in parallel, and they are combined and the circuit is redrawn. The final 3 series resistors are easily combined. Therefore, the Thevenin resistance is equal to 400 ohms. Step 3. Draw the Thevenin circuit. The Thevenin voltage from Step 1 and the Thevenin resistance from Step 2 are used to create the Thevenin equivalent circuit that is shown here. I hope this video has helped you understand how to generate an equivalent Thevenin circuit, as well as understanding that the original circuit and the equivalent Thevenin circuit will deliver the same power to the load resistor. I also hope this video has made Thevenin a lot less sucky. If you find these videos helpful, please like the video, leave a comment, and subscribe to my channel. This is the only way I can continue to make these videos. Tinkercad.com disclaimer. The use of Tinkercad.com in this video is for educational purposes only. Except for the free account I have set up on Tinkercad.com, I have no other affiliation with Tinkercad.com. My use of Tinkercad.com should not be considered an endorsement by me. Tinkercad.com is not sponsoring me or this video in any way. The use of any brand names is for identification purposes only and does not imply any association with the trademark holder. All products and company names are the registered trademarks of their original owners.